Traditionally, when we think about robots, we think about rigid pieces that are linked together, things like C-3PO, things like WALL-E. And what we're trying to do is build robots that emulate biological systems. So they have soft components, they're very deformable, they can squeeze through small spaces, and they can interact safely with people.
And so what we're trying to do is to go away from that a little bit. We wanted to develop tunable stiffness structures and materials, and the idea is that the robot should be soft in situations where we want to conform to the environment or squeeze through tight spaces, but we also would need it to be rigid when we need to apply loads on the environment so that we can adequately push against objects and that sort of thing.
So what we were looking for was a material that could shift between soft and hard states. So what you're looking at here is a soft scaffold of foam that's been coated in wax, and when the wax is heated, you get the soft structure, and when the wax is resolidifies, it regains its rigidity.
So imagine if your components were more compliant and perhaps increase the robot's capabilities. So for example, if you wanted to use this composite foam wax that has tunable stiffness properties to make some autonomous robot or to control the shape of a robot, you can have different segments of the foam coated in wax and selectively change the stiffness of them. So let's say if you have 3 segments and you wanted to just bend the middle one, you keep the outer 2 segments rigid in the cooled state and you heat up the middle one so that it softens, and you can bend it, for example, by pulling a string or a cable that goes down the length just to bend that one. And of course, if you want that shape or that segment to freeze in its new shape, then you let it cool in whatever bent position at room temperature.
I think that the structures you're seeing here are just the beginning of a whole new class of robotics. Again, imagine robots that have the same capabilities of biological systems. Mice, we all know we can't keep mice out of anything because they can squeeze through tiny cracks. This is something that could be useful for robots in search and rescue applications where you have to go through rubble. It could be useful in medical applications where you have to squeeze through small parts of the body. It could be useful in areas where robots have to interact safely with humans. There's a whole host of applications out there.